In 1900, physicist Lord Kelvin gave a lecture at the Royal Institution called 19th Century Clouds over the dynamical theory of heat and light. He identified two unsolved problems hovering over physics. Minor issues, he suggested. Probably manageable. Those two clouds turned out to point directly toward quantum mechanics and relativity. Together, they demolished everything Kelvin thought was settled and rebuilt physics from scratch. This is not a story about right answers, it is a story about theories that worked perfectly, right up until they didn't. This is all of physics, in 20 minutes. Physics is the attempt to describe how everything moves, heats up, glows, attracts, repels, and exists. Every branch started as an attempt to explain something specific, and almost every branch eventually hit a wall where the explanation stopped working. What happened next was always the same. Someone found a deeper theory that explained why the old one worked and also explained what the old one couldn't. Each theory is not simply wrong. It is a special case, an approximation that holds inside certain limits and quietly fails outside them. Keep that pattern in mind. It explains everything that follows. Start at the beginning. The useful beginning. Isaac Newton, 1687. 3 laws of motion, a law of universal gravitation, and the framework of calculus, which he invented partly to do the necessary calculations. Force equals mass times acceleration. Every action has an equal and opposite reaction. Objects in motion stay in motion and stay in motion unless something acts on them. Gravity is an attractive force between any two masses, proportional to their masses, and inversely proportional to the square of the distance between them. This was a machine for predicting the future, disguised as a description of how things fall. Give Newton the position and velocity of every object in the universe at a single moment, and in principle his equations could tell you where everything would be at any past or future time. French mathematician Pierre-Simon Laplace took this to its logical extreme. A sufficiently powerful intellect, given the complete state of the universe, could compute every event that had ever happened or ever would. Physics as total prophecy, it worked staggeringly well. Newton's equations predicted the motion of the planets with enough accuracy to navigate ships across oceans without landmarks. Edmund Halley used them to predict that a comet seen in 1602 would return in 1758. It did, on schedule. His name is on it. The same equations that described a falling apple also described the orbit of the moon, the trajectory of a cannonball, and the path of a distant planet. Two phenomena that seemed completely different turned out to be the same thing described by one rule. That is what a great theory does. It reduces two mysteries to one. For about 200 years, Newtonian mechanics was the foundation of everything. Physicists used it to calculate, predict, and engineer with extraordinary success. In 1846, astronomers noticed that Uranus was not quite following the orbital path Newton's equations predicted. Rather than conclude Newton was wrong, they calculated where an unknown planet would have to be to cause the discrepancy, pointed a telescope there, and found Neptune. Newton's framework was precise enough to discover a planet nobody had seen, using pure calculation. Then heat showed up. Thermodynamics emerged in the early 1800s, driven by an urgent practical problem: steam engines. They were running factories across Britain, and nobody could fully explain why some designs were more efficient than others, or whether efficiency had a theoretical ceiling. The core question was, what is heat, and how does it relate to mechanical work? The answer was built piece by piece over several decades by Carnot, Joule, Clausius, and Kelvin. It came out as 4 laws. The 0th law establishes that temperature is a consistent measurable quantity. If 2 objects are each in thermal equilibrium with a third object, they are also in equilibrium with each other. This sounds obvious, but it needed to be stated. The 1st law says energy is conserved. It cannot be created or destroyed, only converted between forms. Heat is a form of energy. Mechanical work is a form of energy. They can be traded, but the total is always the same. This is why perpetual motion machines do not exist and never will. They would require creating energy from nothing, which the universe does not allow. The 2nd law is where things get philosophically uncomfortable. Entropy, a measure of disorder, or the number of possible microscopic arrangements a system can have, always increases or stays the same in a closed system. Heat flows from hot to cold, never spontaneously the other way. A glass dropped on a floor shatters into many pieces. Nobody has ever watched shards on a floor spontaneously assemble back into a glass. You can burn wood and produce ash and smoke and heat. You cannot reassemble ash and smoke and heat back into wood. Processes in nature are not reversible. The universe tends, overwhelmingly, from order toward disorder. This implies that time has a direction. And here's the strange part. Newton's equations are perfectly time reversible. Film a planet orbiting a star, then play the film backwards and it still obeys Newton's laws exactly. But film a building burning and play it backwards, and you get something the universe never produces. Where does the arrow of time come from in a universe governed by laws that work equally well in both directions? That question is not fully resolved. Thermodynamics describes the arrow of time statistically, but cannot fully explain where it comes from. Put a pin in it. The third law of thermodynamics says that as temperature approaches absolute zero, entropy approaches a minimum. You can get very close to absolute zero, but you cannot reach it. The coldest temperature ever produced in a laboratory as of the mid-2020s was around 38 picokelvin, which is 38 trillionths of a degree above absolute zero. The universe in deep space, by comparison, sits at about 2.7 Kelvin. The laws of thermodynamics are not suggestions. They are among the most robustly confirmed constraints in all of science. James Clerk Maxwell invented a famous thought experiment in 1867 to probe this. Imagine a demon at a small door between two chambers of gas, sorting fast-moving molecules to one side and slow ones to the other. The hot side gets hotter, the cold side gets colder. Entropy seems to decrease for free. The resolution, which took nearly a century, is that the demon must record information about every molecule it sorts, and erasing that stored information costs exactly as much energy as was saved. Information and thermodynamics are physically linked in a way nobody predicted. That connection runs deep into modern physics and computer science. Maxwell himself gave physics its next great unification in 1873. Electricity and magnetism had been studied separately for decades. Faraday had shown experimentally that they were related. A changing magnetic field creates an electric current, and a moving electric charge produces a magnetic field. Maxwell took Faraday's observations and converted them into four equations that describe both electricity and magnetism as aspects of a single electromagnetic field. Then Maxwell did his arithmetic and found something nobody expected. His equations predicted that a disturbance in the electromagnetic field would propagate outward as a wave, and he calculated that wave's speed as approximately 300,000 kilometers per second. He knew the measured speed of light was also approximately 300,000 kilometers per second. He wrote that it was scarcely possible to avoid the conclusion that light is an electromagnetic wave. Radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays are all the same phenomenon. Electromagnetic radiation. They differ only in frequency, which is why your phone receiving a text message and a nuclear explosion are, at the deepest level, the same kind of event at very different energy scales. This was the second great unification in physics. Electricity, magnetism, and light all turned out to be one thing, but Maxwell's equations immediately created a serious problem. They predicted a specific fixed speed for electromagnetic waves. Every wave that physicists knew about traveled at a fixed speed relative to some medium, sound relative to air, water waves relative to water. The assumption was that electromagnetic waves traveled through a medium called the luminiferous ether, a substance filling all of space that served as light's carrier. Nobody had ever detected the ether. It was simply assumed to exist. In 1887, Albert Michelson and Edward Morley built a precision interferometer to measure Earth's motion through the ether. As Earth moves through the ether, light traveling in the direction of motion should be slightly slower than light traveling perpendicular to it, just as swimming upstream is slower than swimming across a current. They measured carefully. They found no difference, none. Earth appeared to be perfectly stationary in the ether regardless of which direction they measured. This is the most consequential null result in the history of experimental physics. The ether did not exist, but Maxwell's equations still predicted a fixed speed for light, and they still worked perfectly. Something in the foundations of physics had to be wrong. What turned out to be wrong was the assumption that time and space are fixed and universal. Albert Einstein, in 1905, took Maxwell's equations seriously and asked what followed logically from the principle that the speed of light is the same for all observers. The answer was strange. Time itself must slow down for moving objects. Space must contract in the direction of motion. These are not illusions or measurement artifacts, they are real physical effects. A clock aboard a fast-moving spacecraft genuinely ticks more slowly than an identical clock left on the ground. GPS satellites experience measurable time dilation due to their orbital velocity, and if their clocks were not corrected for this, the system would accumulate errors of several kilometers per day. Relativity is not a curiosity. It is an engineering requirement. Mass and energy, Einstein showed, are different forms of the same thing, related by the speed of light squared. The c-squared factor is why nuclear weapons and nuclear reactors are possible. A small amount of mass corresponds to an enormous amount of energy. The sun converts approximately 4 million tons of mass into energy every second through nuclear fusion. It has been doing this for about 5 billion years. In 1915, Einstein extended his work to gravity. In general relativity, gravity is not a force that acts across empty space. Gravity is the curvature of space-time produced by the presence of mass and energy. A massive object like the Earth bends the space-time around it, and everything nearby follows the straightest possible path through that bent geometry. The Moon does not orbit the Earth because Earth is pulling it. The Moon follows the path that straight lines take in curved space-time, which happens to loop around the Earth. Light bends around massive objects for the same reason. In 1919, Arthur Eddington photographed stars near the edge of the sun during a total solar eclipse and found their apparent positions were shifted exactly as general relativity predicted. Newton was not wrong. Newton was an extraordinarily good approximation that holds completely at low speeds and weak gravitational fields and fails outside those conditions. This is the pattern. Now back to 1900, because something was already breaking well before Einstein touched it. Classical physics had one more serious problem that had been quietly accumulating. The stability of atoms made no sense. An electron orbiting a nucleus is a charged particle undergoing acceleration. Classical electromagnetism says that an accelerating charged particle must radiate energy continuously. If that is true, every electron in every atom should be spiraling inward, losing energy as radiation, and colliding with the nucleus within a tiny fraction of a second. Matter as we know it should be instantaneously unstable. Atoms should not exist. Clearly they do, which was embarrassing for classical physics and remained unexplained until quantum mechanics arrived. Physicists in the late 1800s were trying to calculate the spectrum of light emitted by a hot glowing object, how much energy at each wavelength, and how that distribution changes with temperature. Classical physics produced equations that matched the data at long wavelengths and failed completely at short ones. As wavelength decreased toward the ultraviolet, the classical prediction rose toward infinity, not a large number. Literal infinity. An everyday object at room temperature should, according to classical physics, radiate infinite energy in ultraviolet and beyond. This was called the ultraviolet catastrophe, and the name is not hyperbole. Max Planck solved the problem in 1900 with an assumption that deeply bothered him. He proposed that energy could only be emitted or absorbed in discrete packets, proportional in size to the frequency of the radiation. He called these quanta. The assumption made the equations match the data perfectly. Planck believed this was a mathematical convenience, a trick to make the numbers work, not a statement about the physical structure of reality. Einstein showed in 1905 that it was not a trick. Light itself travels in discrete packets, photons, each carrying energy determined by its frequency. The photoelectric effect, in which light shining on metals ejects electrons in ways classical wave theory could not explain, was fully accounted for by this. Einstein received the Nobel Prize for this discovery, not relativity, the photon. Once physicists accepted that energy was quantized, the consequences were enormous. Electrons and atoms can only occupy specific energy levels, which is why each element produces a unique spectrum of light when excited. Werner Heisenberg formulated the uncertainty principle. The position and momentum of a particle cannot both be precisely known simultaneously, not because of measurement limitations, but because nature genuinely does not define both at once. Erwin Schrödinger wrote the wave equation describing how quantum systems evolve. And the double-slit experiment demonstrated that a single electron, fired at a barrier with two openings, passes through both simultaneously, interferes with itself, and lands on the far screen at a location determined by probability rather than a definite path. When a detector is placed to observe which slit the electron uses, the interference vanishes. The act of measurement changes the outcome. This is the measurement problem, and 100 years later, nobody has fully explained it. Mathematics of quantum mechanics describes a particle as a wave function, a spread of probabilities across possible states. The wave function evolves smoothly and deterministically, according to Schrödinger's equation. But when a measurement happens, the wave function collapses to a single outcome. The Schrödinger equation does not contain a collapse. It is added as a rule, what physically happens during measurement, who counts as an observer, and why the universe looks definite at large scales when it is fundamentally probabilistic at small ones. These remain open questions. Physicists use quantum mechanics every day without agreeing on what it means. That is unusual in science and says something interesting about both physics and physicists. Quantum mechanics gave the world transistors, lasers, MRI machines, LEDs, and atomic clocks. Every digital device you own operates on principles derived directly from it. It is the most precisely tested theory ever formulated. So physics now has two frameworks, each perfect in its domain. General relativity describes the large. Gravity, space-time, galaxies, black holes, the expansion of the universe. It treats space-time as a smooth, continuous, geometric entity. It has never failed an experimental test. Quantum mechanics describes the small. Particles, photons, forces, probability, uncertainty. It treats the world as discrete, probabilistic, and deeply strange. It has also never failed an experimental test. Try to use both at the same time and the equations break. General relativity requires spacetime to be smooth and continuous at every scale. Quantum mechanics predicts that at the smallest scales, spacetime itself should be subject to quantum fluctuations, grainy and uncertain. Applying the mathematical tools of quantum field theory to gravity produces equations full of infinities that cannot be systematically removed. String theory proposes that fundamental particles are tiny vibrating strings whose different modes of vibration produce different particles, and that the additional dimensions required by the math are curled up too small to detect. Loop quantum gravity proposes that spacetime is itself made of discrete quantum units rather than a continuous fabric. Neither approach has produced a confirmed experimental prediction. The unification project has been running for 90 years. Kelvin said physics was done at 1900. Physics proceeded to overturn every foundational assumption he held. The nature of time, the structure of space, the behavior of matter at small scales, the relationship between mass and energy, the existence of a universal speed limit, the connection between information and thermodynamics. All of it was upended between 1900 and 1930. Each overturned assumption produced a better theory. Each better theory still broke down somewhere. Each breakdown pointed towards something deeper. The two theories we have now are the most accurate descriptions of physical reality ever produced. They are also incompatible. That is not the end of physics. That is physics telling you, in the only way it knows how, that there is something left to find. And that is all of physics, more or less. In 20 minutes. Kelvin would disagree, but he has already been wrong once today.